All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. We're in topic 6.8 now in thermochemistry, and we're looking at now enthalpy of formation. Okay, and this is going to be another way that we can help determine the overall enthalpy of a reaction. Now, this is going to correspond to section 5.7 in our Brown and LeMay textbook. So if you need to reference that, feel free to go read that content, read that section to help give you a better idea of some of the things that we're talking about. It's going to provide you some more context, maybe give you a little bit more information if you'll find that helpful. And so before we get into even doing the calculations, we need to talk about what do we mean when we say the enthalpy of formation. We understand enthalpy, the heat of a reaction, the energy that's required for a reaction to take place, or the energy changes that take place. But what is this idea of enthalpy of formation? What does that mean? Well, enthalpy of formation is a specific form of enthalpy. And so enthalpy of formation is delta H sub F. Now, this is going to be defined as the enthalpy change for a reaction in which a compound is made from its constituent elements in their elemental forms. All right. Now, you might be thinking, Mr. Kenton, I understand all of those words, but that doesn't make a lot of sense to me. So I want you to think about it from this particular perspective. What we're saying is, let's pick a compound. Like we're looking at the table over here. Let's pick ammonia. So ammonia is NH3 as a gas. Okay. And they're saying the enthalpy of formation is the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. Well, our compound is ammonia, NH3. Well, the elements that make up NH3 are nitrogen and hydrogen. So that means the reaction we'd be looking at is nitrogen gas plus hydrogen gas. Right? So this particular reaction, I know it's not balanced yet, but this particular reaction would represent the enthalpy of formation equation because we took the individual elements, nitrogen and hydrogen, that made this substance to get its energy. So that'd be the enthalpy of formation. Now, for this particular case, to balance it, we'd have a 2, a 3, and we'd be done. So this would be the enthalpy of formation equation for this particular reaction, right? So that'd be delta HF. Okay. So that's what enthalpy of formation is. Now, if you look at this table, it says standard enthalpies of formation. You're like, all right, Mr. Kenton, goodness, why do we have to have enthalpy of formation versus standard enthalpy of formation? What's the difference? So notice here, delta H sub F, and then it's got that little degree symbol. That's the standard enthalpy of formation. Now, delta H sub F naught, as it's commonly referred to, is going to be the change in enthalpy for the reaction that forms, now catch this, specifically 1 mole of the compound from its elements with all substances in their standard states at 25 degrees Celsius and 1 atmosphere of pressure. Okay, so now when we look at this particular reaction, this was our delta H sub F, right? It was the enthalpy of formation because we made the compound from its elements, but notice here, we made 2 moles. But to get the standard enthalpy of formation, we need to make only 1 mole. So if we wanted to represent that reaction as a standard enthalpy of formation reaction, we go back, we got N2 as a gas plus H2 as a gas produces NH3 as a gas. Right, so we want 1 mole, but again, we still got to make sure that it's a balanced equation. And this is when things get a little funky, right? So this is one of the few times that we can do this. We're gonna be able to balance this with fractions. I know, don't freak out. So if we want it to make just simply 1 mole, well, that means we're going to need half a mole of nitrogen, and then we're going to need 3/2 of H2 to make 1 mole of NH3. So this particular chemical reaction would represent the delta H sub F naught of that particular process, because we made 1 mole of ammonia from its elements that were at their standard states. Now, standard states simply mean what physical state will that substance be at 25 degrees Celsius in 1 atmosphere of pressure. Now, a note here when you're looking at enthalpies of formation, because you're going to be provided a table here that you're going to use as a reference. And something you need to remember is that elements that are in their standard state are going to have an enthalpy of formation of 0, because that's how they naturally occur. They don't require any energy changes for them to exist that way. And so, as a result, there's going to be no energy change. So, like, for example, if you looked up the standard enthalpy of formation of nitrogen gas or hydrogen gas, it wouldn't be in the table, but even if it were, it'd have a value of 0. So just to reiterate that last point there, the standard enthalpy of formation for the most stable form of an element is 0. And the reason for that, there's no formation reaction needed for an element that's already in its standard state, because that's how it naturally exists, right? And a good example of this, like if you look at this chart, if you find diamond has an enthalpy of formation of 1.88 kilojoules per mole. So that's telling you is that diamond is not the natural form that carbon exists in. Carbon naturally exists as graphite, and so the enthalpy of formation for graphite would be 0, right? I hope that makes sense. So you've got this as your backdrop. We've got enthalpy of formation. Doesn't matter how much of the compound you're making, as long as it's made from its elements, that'd be an enthalpy of formation. But the standard enthalpy of formation is when you specifically make 1 mole of product from the elements in their standard states of that same substance. I hope that makes sense. Now, we can use enthalpies of formation as a way to calculate delta H. Now, we've already seen this already when we introduced bond enthalpies, but we know in chemical reactions, in order for them to occur, bonds have to be broken and new bonds have to be formed, right? And we even introduced this idea that breaking a bond is endothermic. It requires energy to do so, it requires energy to break a bond, and that forming a bond is going to be exothermic. All right, let's correct this right here, right? So it says bond forming is endothermic. That's false. Let's fix that. Bond forming is exothermic. Okay, so that's a negative delta H value. Now, the standard heat of reaction is the sum of the standard heats of formation of the products minus the standard heats of formation of the reactants. All right. So delta H naught is going to be equal to the sum, of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. And keeping in mind here, N and M are going to be the stoichiometric coefficients of each of your individual products and reactants in your balanced chemical equation. Okay. And so this is going to be an important equation that we need to be familiar with and how to use. Again, we use this when we're using the standard heats of formation or standard enthalpies of formation, right? So elements in their standard states making 1 mole of their compound, right? Take a look at an example here. So let's consider the reaction of propane reacting with oxygen to make carbon dioxide and water. Now, please note physical states, very important here, because your enthalpies of formation are going to be based off of those physical states that we're talking about. So what we can do is we can use the heats of formation for each substance to estimate the enthalpy of reaction. So delta H naught, go ahead and just put those there. is going to equal the sum of the enthalpies of formations of the products minus the sums of the enthalpies of formation of the reactants. Now, if we want to think about how we get there, we do products minus reactants. So we look, it's going to be 3 times the enthalpy of formation of carbon dioxide plus, and again, that 3 is the coefficient, so that's why it's 3 times that, plus 4 times the enthalpy of formation of liquid water minus 1 times the enthalpy of formation of propane, C3H8, plus 5 times the enthalpy of formation of O2. Now, since oxygen is an element in its standard state, that's why it's going to have a value of 0. So we can just go ahead and ignore that. So then in our next step, we can then plug in our numbers from the table. So we got, this is the enthalpy of formation of carbon dioxide, enthalpy of formation of water, enthalpy of formation of propane. So we multiply our terms, we get our values, eventually we combine everything, and what we see here is that after this reaction takes place, it should release, or we can estimate it as minus 2,219.9 kilojoules. So this particular reaction, the reaction of propane, is exothermic. Okay. And again, in order to get these numbers that I underlined in step 3, you would look at a reference chart that would give you the enthalpies of formation of each of the substances we listed. Carbon dioxide as a gas, water as a liquid, and propane as a gas. All right. And that, ladies and gentlemen, is how you can use enthalpies of formation to estimate the enthalpy, the standard enthalpy of a reaction. Okay. So thank you so much for watching this video. I hope it was insightful, hope it was helpful. If you have any questions, please don't hesitate to reach out to me. You know how you can contact me. You can email me. You can ask me questions in class. Just let me know. Again, thank you so much. Hope this was helpful, and I'll see you guys again soon. Take care.